OCR Chemistry A, carboxylic acids and esters. Using Chemistry Explained means that you write notes on paper or tablet. You control the pace of the lesson through pausing or replaying the slides. Most important, when prompted, complete the task, thinking the problem through, taking your time before you check against the correct answer and then move on. We'll start with the naming of carboxylic acids, move on through acidic properties and reactions, solubility, forming and hydrolysing esters, acyl chlorides, and then acid anhydrides. So naming carboxylic acids, which in OCR A are regarded as a combination of the carbonyl group and a hydroxyl group. So here is the generalized structure, and systematically they're called alkanoic acids, although OCR A continues with the traditional carboxylic acid naming. The carbon of the carboxyl group is always numbered number 1 in any carbon chain. Try naming this carboxylic acid. So I will reveal. This is butanoic acid. So carbon number 1, 2, 3, 4, 4 carbons in the chain, butanoic acid. I'd like to name this example, these two examples. Come back when you're ready to check your answer. Okay, so revealing 2-methyl-butanoic acid, carbon number 1, 2, 3, 4. The longest chain is 4, so that's butanoic acid on carbon number 2. There's a methyl group, 2-methyl-butanoic acid. And then over here, 3-chloropropanoic acid, carbon 1, carbon 2, carbon 3, gives us propanoic acid. There's a chlorine atom on the third carbon in the chain. So 3-chloropropanoic acid. Alicyclic and aromatic carboxylic acids are named by adding carboxylic acid to the structure name. For example, here we have cyclohexane, so this would simply be cyclohexane carboxylic acid. If you'd like to try and name the two other examples, pause, come back to check your chemistry. Okay, so here we have a benzene ring, so it's very simply benzene carboxylic acid. Here we have a benzene ring carboxylic acid, but also a hydroxyl group. The positioning of the carboxylic acid defines carbon number 1, so this is carbon number 2. So this is 2-hydroxy benzene carboxylic acid. It's always the case that the carboxyl group defines carbon number 1. So in this case, we're going to say the carboxyl group, the carboxylic acid group, is attached to carbon number 1 in the benzene ring. So, what about structures like this? So we've got a carboxylic acid, carbon, CH2, and then the benzene ring. Well, you may recall from the naming of aromatics that we'd regard this as a side chain containing a functional group, so the benzene ring is named as phenyl. So this would be 2-phenyl ethanoic acid, carbon 1, carbon 2 in ethanoic acid, the phenyl group is attached to carbon number 2. So 2-phenyl ethanoic acid. You will also meet dicarboxylic acids in polymerization and in some titration problems. They're named as alkane dioic acids. So let's look at an example. We've got 6 carbons in the chain. We've got 2 carboxyl groups at each end of the chain. So we would name that as hexane dioic acid. The carboxyl group is always at the end of the chain. So we define the longest chain, or the parent molecule, by the presence of 2 carboxyl groups. So this is hexane dioic acid. Example on the right hand side contains a benzene ring. Would you like to pause and try and name this? Okay, so to reveal, it's benzene 1,4-dicarboxylic acid. So if we just had a single carboxyl group, that would be benzene carboxylic acid. So it's benzene dicarboxylic acid, but we need to define the distance apart, the spacing of the carboxyl groups around the benzene ring. So carbon 1, carbon 2, carbon 3, carbon 4. So benzene 1,4-dicarboxylic acid. So a review of acidic properties and reactions of the carboxylic acids. Of course, carboxylic acids are weak Bronsted-Lowry acids. So for Bronsted-Lowry acid-base theory, we need both an acid, a proton donor, and a base, a proton acceptor. So in solution, of course, water acts as the proton acceptor. The electrons that were in the bond here, of course, now appear as a lone pair here. The proton, the acidic hydrogen within the carboxylic acid, ends up in being datively covalently bonded to the water molecule to form the hydronium ion. Now, of course, the position of equilibrium lies well to the left. So the concentration of the hydronium ion is very low compared to the concentration of the weak, or the carboxylic acid. However, carboxylic acids react with bases and metals according to the balancing of the equation, that is the stoichiometry. So for example, if we took propanoic acid and sodium hydroxide to make the salt and water, then the reacting ratio is 1 mole of propanoic acid reacts with 1 mole of sodium hydroxide. That reacting ratio is not affected by whether propanoic acid is a weak or strong acid. It's still a 1-to-1 ratio as per the stoichiometry, or the balancing of the equation. Now, the salt product here is named as an ester. So we have the propanoate and sodium, so we would call that sodium propanoate. So moving on to some reactions of the carboxylic acids with metals, carbonates and alkali. Could you complete balanced symbol equations for the 3 examples there? Pause, come back to check your equations against mine when you are ready. So if we look at magnesium, we will form, with propanoic acid, we will form magnesium propanoate, 2 propanoate ions. The propanoate ion is formed from propanoic acid by the loss of the acidic hydrogen. So we have a 1- propanoate ion. So we need 2 of the propanoate ions to combine with 1 magnesium 2+ ion from group 2. Note the product of a metal acid reaction is hydrogen and not water. 2 propanoic acids needed to balance. If you're ready, we'll move on. Calcium carbonate and ethanoic acid gives us calcium ethanoate. Again, the ethanoate ion is 1-, calcium a 2+ ion from group 2. On this occasion, the product is water. It is a neutralization. But in addition, with a carbonate, we get carbon dioxide and 2 ethanoic acids required to balance. Our third, sodium hydroxide and ethane dioic acid. So ethane dioic acid has 2 acidic hydrogens, so it will combine with 2 sodiums to form sodium ethane dioate, and 2 moles of water are produced, requiring 2 moles of alkali. Now, which of these is a redox reaction? Well, 2 and 3 are neutralizations, but if we look at the oxidation numbers for reaction 1, magnesium is 0 here, but +2 on the right hand side. Hydrogen, if we just focus on the acidic hydrogen here, is +1 in a compound and 0 as an element. So there's a change in oxidation number, and therefore reaction 1 is not a neutralization, it is a redox reaction. Please also note that the reaction of an acid with or carboxylic acid with calcium with a carbonate or a hydrogen carbonate is the test for that carboxylic acid, and you will see fizzing or bubbles of carbon dioxide being produced. So the test for a carboxylic acid is to mix it with either a carbonate or a hydrogen carbonate and observe the evolution, the bubbling of carbon dioxide. That is a positive test for the carboxylic acid. If we compare the acidity of carboxylic acids to alcohols through the example of ethanoic acid and ethanol, we can see that the pKa value for ethanoic acid is much lower than that of ethanol, and therefore ethanoic acid is much more acidic. We explain that by comparing the stability of the conjugate bases formed. So in Bronsted-Lowry theory, of course, the carboxylic acid donates a proton to the base water to form the hydronium ion H3O+, leaving behind the conjugate base. Now the conjugate base is negatively charged. If the charge is located on one oxygen atom, that is less stable than if that negative charge could be delocalized through a number of atoms, for instance, the oxygen-carbon-oxygen system. Because there are p electrons on the oxygen carrying the negative charge on my diagram, these can interact with the pi bonding of the carbonyl, and therefore this negative charge can be delocalized through the 3 atoms by overlap of p orbital electrons. Now that stabilizes the conjugate base, and therefore the equilibrium lies further to the right for a carboxylic acid because of this delocalization than it would otherwise. That delocalization is not available to, for example, the ethoxide ion, and therefore the acidity of carboxylic acid is much greater than that of an alcohol. An explanation of the solubility of the carboxylic acids. The solubility of carboxylic acids depends on the ability to hydrogen bond with water. So if we look at a generalized carboxylic acid structure, I've put in bond polarities across the carbonyl group and marked in lone pairs of electrons on the oxygen of the carbonyl. But I also now bring in a water molecule. You'll see that because there's a very large electronegativity difference between oxygen and hydrogen, hydrogen is strongly delta plus. It's directly bonded to oxygen, which is a requirement for hydrogen bonding. I may remind you, and an electrostatic attraction will form between the highly polarized hydrogen atom and the lone pair of electrons on the oxygen delta minus of the carbonyl. Now, the hydrogen here and the oxygen here can also interact with water in a very similar way. But I've left my diagram simple just by looking at one possible instance. This electrostatic attraction is of course called the hydrogen bond. It is an intermolecular force, the strongest of the intermolecular forces. And substances that cannot hydrogen bond with water or interact with water generally are insoluble, whereas organic molecules that can hydrogen bond with water tend to be soluble. So short chain carboxylic acids are found to be soluble in water for that reason. However, is octanoic acid soluble? Well, it's considerably less soluble than, for instance, ethanoic acid. The influence of the carboxyl group is much reduced the longer the carbon skeleton. So for short chain carboxylic acids are regarded as soluble or highly soluble in water. The solubility decreases as the length of the carbon chain, the insoluble hydrocarbon chain, increases. Forming and hydrolysing esters. Carboxylic acids react with alcohols to form esters. So for instance, propanoic acid, which I've got the skeletal formula here, and ethanol, also skeletal formula, so 1, 2 carbons, 1, 2, 3 carbons, react to form ethyl propanoate and water. The structure looks like this. So the hydrogen from the alcohol and the hydroxyl group from the acid end up forming water. So this oxygen bonds to that carbon. So here is our ethyl propanoate. This section here, okay, corresponds to this section here. So the ethyl bit originates from the alcohol and the propanoate derives from the carboxylic acid on the left. So that's ethyl propanoate and of course water. So it's a condensation reaction with the loss of water. Now the conditions you are expected to know and recall. Hot concentrated sulfuric acid acts as a catalyst. Here are 3 word equations describing esterifications. So we're missing the products in number 1, we're missing the reactants in number 2, and we're missing the products in number 3. Pause and fill in the missing chemical identities. Come back when you are ready to check your chemistry. Okay, so ethanoic acid and methanol. Well, if we follow this pattern, that's going to form methyl ethanoate. So the ethanoate derives from the acid, and the methyl group derives from methanol. Don't forget to balance your equation with water. If you're ready, I'll move on to number 2. So ethyl octanoate and water. So going to derive from octanoic acid, and the ethyl naming means our alcohol was ethanol. If you're ready, I'll move on to number 3. So ethanol and methanoic acid. So ethyl derives from the alcohol and methanoate derives from the acid, methanoic acid. So ethyl, methanoate and water. So esterification can be reversed by the reaction with water. So an ester and water will reform the carboxylic acid and alcohol, an exact reversal of the esterification process. So let's look at an example. Ethyl propanoate, we're going to break the carbon single bond oxygen in the ester, and we're going to add water molecules, or the atoms from the water molecules, across the 2 products, which of course are ethanoic acid, propanoic acid, I beg your pardon. We've got 3 carbons here, so 1, 2, 3, so that's propanoic acid, and we've got 2 carbons here, so this is ethanol. Now, where's the water gone? Well, we've added a hydroxyl group here, and we've added a hydrogen here. So very simple, we're breaking lysis and adding water to reform the carboxylic acid and the alcohol. So if I give you an example, what would be the products of methyl butanoate and water? Predict the hydrolysis products. Okay, so I'm going to reveal methanol from the methyl and butanoic acid from the butanoate. And a second prediction, propyl ethanoate and water predict the 2 products. Pause, come back. Okay, so propyl will become propan-1-ol. You must be clear it's not propanol. It's not enough detail. Is it propan-1-ol? Is it propan-2-ol? So propan-1-ol and ethanoic acid. We need to consider the nature of the catalyst used to carry out or speed the reaction of hydrolysis. That catalyst can either be acidic or alkaline. But there's a complication in that, be it acid or alkali, it may react with the end product of hydrolysis to change that hydrolysis product. For example, alkaline catalysts react with the carboxylic acid product of aqueous hydrolysis. So, if we have an ester and water forming a carboxylic acid and an alcohol, then the carboxylic acid would react with an alkaline catalyst to form, of course, a carboxylate salt. So, for instance, if it was ethanoic acid as the product, we would get sodium ethanoate as the final carboxylate salt. So, fortunately, alcohols, as far as the chemistry is concerned, do not react with alkali. So, an alkaline catalyst only reacts with the carboxylic acid product and not with the alcohol. So, if we look at this as a 2-step process, first of all, the reaction of the ester with water. So here's our methyl propanoate reacting with water to give us propanoic acid and methanol. Well, only the propanoic acid will react with, say, sodium hydroxide present as the catalyst. So our second reaction then would be propanoic acid and sodium hydroxide will give us sodium propanoate and water. So how do we construct that into an overall equation? Well, of course, we draw a line down the middle, and we know we cross off those things that are present left and right. So water is present on the left and on the right, so that's no overall change in the amount of water. We have propanoic acid on the left and propanoic acid on the right. So we are left with methyl propanoate, sodium hydroxide, giving us sodium propanoate, and of course methanol. So our overall hydrolysis equation is this equation at the bottom. But of course, if we think of it as occurring in two steps, we first of all form the carboxylic acid and the alcohol. The carboxylic acid then further reacts with the alkaline catalyst present to form the sodium salt. So when we combine those two reactions, we'll see that overall we have our ester and alkali giving us our sodium salt and our alcohol. Acidic hydrolysis is a simpler situation because acids do not react with either product of aqueous hydrolysis of an ester. An ester and water will form a carboxylic acid and an alcohol. Well, carboxylic acids do not react with mineral acids, and neither do alcohols. So if we look at the acidic hydrolysis of methyl propanoate, the propanoate will become propanoic acid and the methyl part will become methanol. Those are the final products of the hydrolysis. Acyl chlorides. So acyl chlorides are formed by the reaction between carboxylic acids and thionyl chloride, SOCl2. So here's an incomplete word equation involving propanoic acid. Could you predict the name of the organic product? So I'm going to reveal propanoyl chloride. So we name acyl chlorides in the fashion propanoyl chloride. We have the co-products of sulfur dioxide and hydrogen chloride. Could you complete this chemical symbol equation? Come back to check. Okay, so I've got our propanoyl chloride, sulfur dioxide, HCl, so SOCl2. It's all a 1:1:1:1:1 ratio. There is our structure of propanoyl chloride. Carbon, carbon, carbon double bond oxygen, so the carbonyl, and then instead of, for instance, it's often known as an acid derivative, instead of an OH group, we have a chlorine. So there is propanoyl chloride. Could you predict and draw the structures of the products of this reaction? Come back to check. Okay, so if you're ready, of course, we're getting ethanoyl chloride, sulfur dioxide, and hydrogen chloride. Don't forget to balance your equations, please. So acyl chlorides are useful in synthesis because they are more reactive than carboxylic acids. A typical reaction of acyl chlorides, in fact, is the reaction with water, the vigorous reaction with water, to reform a carboxylic acid. So in words, we have, for example, propanoyl chloride and water going to propanoic acid and hydrogen chloride. A simple checking exercise, rewrite that word equation in terms of structural formulae. Pause, come back to check your chemistry. Okay, so if you're ready, CH3CH2COCl, there's propanoyl chloride, so that's carbon, double bond oxygen, carbon, chlorine, and then of course propanoic acid. So there is the symbol equation. Now, the reactivity difference between acyl chlorides and carboxylic acids is explained by considering the bond strengths. Now you can see here the carbon-chlorine bond is the bond I'm concerned with, and the carbon-oxygen bond in the carboxylic acid. These are the bonds that are broken when both acyl chlorides and carboxylic acids react. It's the same bond, the carbon-chlorine from the carbonyl-carbon, or the carbon-oxygen, carbon single bond oxygen from the carbonyl-carbon. Now, the bond length between carbon and chlorine is longer, and therefore the bond is weaker. The carbon-oxygen bond is shorter and therefore is stronger. So as in both cases it's this bond that needs to be broken, as the carbon-chlorine bond is weaker, it's going to be more easily broken. And that makes acyl chlorides more reactive than the carboxylic acid. So let's look at some reactions of acyl chlorides, which, as I've mentioned, are very similar to those of carboxylic acids, but are more vigorous. So acyl chlorides esterify with alcohols. So here we have our propanoyl chloride, and here is ethanol. Can you predict the structure of the ester formed and identify the co-product? Pause, come back to check. Okay, so I'm assuming you're ready. We have our ester, again, these two carbons from the alcohol form the ethyl part of the ethyl propanoate. The end product is not water, but is hydrogen chloride. So we're taking a hydrogen from the alcohol and the chlorine from the acyl chloride, and those are combining to form hydrogen chloride. So it is still a condensation reaction, but the small molecule that is lost is hydrogen chloride. To example the increased reactivity of acyl chlorides, there is no catalyst required for this esterification, whereas I will remind you with carboxylic acids, concentrated sulfuric acid or hot concentrated sulfuric acid is required. There is no catalyst with an acyl chloride. So that is a similar reaction to the reaction of carboxylic acids with alcohols. However, carboxylic acids do not react with phenols, whereas acyl chlorides do. So here is phenol, here is an acyl chloride. Can you predict the structure of the product? Pause and then come back. Okay, so if you're ready, here is our ester product, and of course hydrogen chloride is the small molecule eliminated. Just to repeat and emphasize, the exam board emphasizes this as well. Carboxylic acids do not react with phenols. They are not reactive enough. Acyl chlorides have to be employed as they have sufficient reactivity. So let's move on to the reaction of acyl chlorides with excess ammonia to form the amide. Starting again with propanoyl chloride, this time reacting with ammonia, could you complete the structures and identify the products? Pause, come back when you are ready. Okay, so we're going to get a straight substitution an elimination of the chlorine, and that's going to end up in hydrogen chloride. One of the hydrogens from here is going to end up here. So we've now got our amide. So here is our amide. Now, if we look at that as a chemical reaction, we will see that the propanoyl chloride plus ammonia gives us our propanamide and hydrogen chloride. Now, the exam board wish you to realize that hydrochloric acid, HCl, is of course going to react with the excess ammonia. So we have excess ammonia. So a second equation then follows. HCl and NH3 goes to ammonium chloride. So overall, we're going to achieve that as the overall equation. We have propanol chloride on the left-hand side, doesn't appear on the right. Ammonia twice on the left-hand side. Propanamide, ammonium chloride, and of course, what does cancel out left and right is of course HCl. So our overall equation is propanoyl chloride plus 2 ammonias gives us propanamide and ammonium chloride. So moving on to the reactions of acyl chlorides with amines, and we can use the reaction of acyl chlorides with ammonia as our model. So here's propanoyl chloride with a primary amine. Can you predict and draw the structure of the amide product and any other co-product? Come back when you are ready. Okay, so I'm going to reveal. Here's my amide, and my co-product is the small molecule hydrogen chloride. So this is a condensation reaction again with the elimination of hydrogen chloride. Now here we have a secondary amide. The nitrogen here is bonded to 1 carbon, is bonded to 2 carbons. So that is a secondary amide. Carbon double bond oxygen, carbon nitrogen, nitrogen carbon, nitrogen hydrogen. That is a secondary amide. If we write the equation in terms of structural formulae, we can see the propanoyl chloride and the amine gives us our secondary amide and hydrogen chloride. Now, the exam board expects you to realize that hydrogen chloride will react in an acid-base, a Bronsted-Lowry acid-base reaction with the amine. The amine contains a nitrogen with a lone pair of electrons, so it's a proton acceptor. So a second equation would give us hydrogen chloride and the amine, giving us our amine-derived ammonium chloride. Could you deduce or calculate the overall reaction equation for the reaction between propanoyl chloride and excess primary amine? Come back to check when you're ready. Okay, so revealing. Secondary amide and of course our ammonium chloride product. Our last section now, acid anhydrides. Acid anhydrides are formed by the dehydration of carboxylic acids. The reagent, hot concentrated sulfuric acid, is not required in the OCR Chemistry A specification. However, the equation here may well be. 2 ethanoic acids, for example, gives us ethanoic anhydride, and a water molecule is eliminated. Could you pause and draw the structure of ethanoic anhydride. Come back to check in a moment. Okay, so I'm going to start off by drawing or revealing two structures of ethanoic acid, and I'm going to suggest that it's those atoms that are lost to form this water molecule, which explains how this structure is derived. So this oxygen bonds to this carbon. So we have the ethanoic anhydride structure. Now, that may be drawn as a skeletal, which I've put inside a red box here. So carbon, carbon, double bond oxygen, carbon single bond oxygen, oxygen single bond carbon. So there is ethanoic anhydride as a skeletal. Now, what's useful about anhydrides is that they are less reactive than acyl chlorides, but have the same range of reactions. Acyl chlorides react very vigorously. It may be wiser to react with an acid anhydride. So acid anhydrides are less reactive than acyl chlorides, but have similar reactions. For example, acid anhydrides will react with phenols to make an ester and carboxylic acid. And you may have made aspirin through the reaction of ethanoic anhydride and phenol derivatives such as salicylic acid. So let's take ethanoic anhydride and phenol. Could you draw the displayed structure for the ester and for the carboxylic acid that would form? Come back to check against my chemistry when you are ready. So revealing, here is the carboxylic acid. What we've done is broken this bond here, and we've taken this section of fragment of molecule and taken this hydrogen to form ethanoic acid. The rest of the molecule joins to form the ester. Similarly, acid anhydrides react with alcohols to form an ester and carboxylic acid. So if this time I give you some structural formulae, so here's propanoic anhydride and here is methanol, can you suggest the structure of the ester formed and of the carboxylic acid? Pause, complete the task, come back to check when you are ready. Well, the ester formed is of course methyl propanoate, and the carboxylic acid is propanoic acid. Just to emphasize, you have met acid anhydrides because they are less reactive than acyl chlorides and therefore safer and more suitable for school laboratories. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you, but those sources which have comprehensive answers are the best. So attempt the problems, check your answers. Move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.